So I'm super excited to introduce Danqi Chen. She's currently a visiting scientist at Facebook AI Research in Seattle, soon to be assistant professor at Princeton. Her work is really well known at the intersection of machine learning, information extraction, knowledge-based completion, more recently, the super related areas of reading comprehension and question answering. And her work has been recognized with Best Paper Awards at ACL and EMNLP. And she was recently in Amherst last spring for a faculty interview. And I joined for breakfast one day, and someone else who was at breakfast, asked her for advice on how did she choose these really awesome, research projects, research problems that are really well recognized. And her advice was super simple. And she said it much more eloquently, I'm sure, than I'm going to say it. But she basically said, not to focus on doing incremental work, but instead to choose important problems where your work will really change how people view the research area, I guess. So given that, I'm really excited to hear about what she's been working on. So welcome, Danqi Chen.
Thanks, Emma, for the kind words. Actually, I'm not sure if I still remember I said something like that last year. So thanks for having me here. So it's really great for me to come back to AKBC. I also co-organized the last 2 AKBC workshops. So as Emma introduced, so I currently work for Facebook, and I graduated from Stanford University a couple months ago, and I will be joining Princeton University this September. So most of the things I'm going to talk about today is still from my PhD research, but I'll be very happy to chat about what I'm up to at Facebook. So actually, I will start with a question that Chris Manning asked in the AKBC 2013 workshop. So can knowledge base be just our text? So actually, 2013 is a year that I started to do research in natural language processing. And at that time, there was not too much deep learning for NLP yet. So right now, 6 years have already passed. And today I would like to re-examine this question. So what is our reality today in 2019? So how far are we still from this goal? Can knowledge base be just our text? So here is generally a big picture. So if we want to extract knowledge and the information from the text, there are generally 2 paradigms we can approach this problem. So one paradigm is more traditional knowledge-based construction paradigm, that we want to extract information from text and also other modalities to build a structured knowledge base. Then we can actually reason over this large-scale knowledge graph and answer questions based on it. And the other paradigm is that we can actually just bypass the whole knowledge-based construction process. And we just want to build systems to directly read the text and reason over the text directly. So I call this second paradigm as machine reading. So these 2 paradigms have coexisted for quite a bit of time. So they both have advantages and disadvantages. So we know this structured knowledge bases, usually we can have curated a very high quality and clean facts, but they also suffer from this fixed schema problem. So they only can support a limited set of questions that actually can be answered by this knowledge bases. But also a great advantage of the knowledge base is that they are actually much easier to store and reason. So for some question, today we still believe, for example, what is the population of the second largest city in California? These kind of questions will be still easier to be answered by knowledge base, that we can actually convert this question into some kind of logic form that actually can be executed against the knowledge base and get the answer. I believe it's San Diego in this case. So for the second machine reading paradigm, so we want to directly read the text and reason over the text. So text has a much better coverage, but it's also it has a lot more variety and also much flexible and then also harder to handle with. So we can argue that machine reading is actually a harder problem in this paradigm. But text has this great advantage that they can cover a lot of facts that are much better than what the large base can cover. So for some question like, what is the best time for whale watching or moai? So for this kind of question, we cannot just find a relation in the large base. And this kind of question can be much easier to be answered by text. So actually, where is the boundary today between these two paradigms? So let's try to ask some questions on Google and see what Google does today. So if we want to ask a question like, when is Stanford's commencement in 2019? Google can actually return this correct answer on June 16, 2019. But you can see that this answer is actually exactly extracted from this snippet from this web page, and not actually exactly using the Google's large graph. So the answer is actually contained in the text, like join us for Stanford's 128th commencement ceremony on Sunday, June 16th, 2019. So I tried to ask another question yesterday. So where is AKBC 2019 held? So you can see that Google also gives us the correct answer, the University of Massachusetts Amherst. But you can see that this is actually a fact stored in the large base. It's actually I'm not sure why this answer cannot be extracted by text, but this is what actually Google does today. So for this talk, I will only focus on this second paradigm, machine reading. So my biggest goal of this talk is to give you a high-level overview about, as a community, how far has machine reading gone so far in the last few years, especially in the context of the deep learning and the deep neural networks. So what are the main challenges and the problems we are still facing today? And hopefully at the end, I will come back to this question. So what is actually still the boundary between these two paradigms, using the structured large base or just using machine reading? So I'll take a step back and try to give a definition of what is machine reading. So at a high level, the goal of machine reading is that we actually want to build models that can read text, represent the information contained within the text, and answer questions based on this representation. So I'll talk about an even more narrow sense of the machine reading today, that we formulate machine reading as a supervised reading comprehension problem. So the task can be formulated in this way, that the input is a document and a question about the content of the document. So we want to build models that actually can read this document and understand the information contained in the document and answer question about the document, and then finally return this answer. So I talk about this as a supervised problem because the input to this system is actually the document question and answer triples. So here we can assume the document as either a simple paragraph or a document, or actually a collection of documents. I will give you some more concrete examples of what, as a community, what problems we are trying to solve in this machine reading context. So this is the most famous popular data set called Stanford question answering data set, SQUAD. So the document is like short paragraph text. And we want to ask questions like, which team won Super Bowl 50? And the system needs to read this text and find out the American Football Conference champion Denver Broncos defeated the National Football Conference champion Carolina Panthers, 22 blah blah, and finally found out the answer to this question, the champion is the team is actually Denver Broncos. So there are more challenging problems we are trying to tackle. So this is a very new data set called JOBS by Matt and Samir and other people in Allen Institute. So we actually want to build these machine reading systems to actually solve some even challenging problems that actually require some discrete reasoning. So here's an example. That the question is, how many more dollars were the untitled painting sold for more than $12 million estimation? So if we want to get this question correctly, the system actually needs to find out the last sentence. So this painting was sold by Robert for $16.3 million, well above its $12 million high estimate. And the system actually needs to understand this sentence and then perform some sort of like subtraction, extract these two numbers, and then perform some sort of subtraction, and then finally return this answer, 4.3 million. So there are actually even some more challenging problems in machine reading that we actually want to build systems not to only understand just one single paragraph. We actually want to build systems to read multiple documents, to actually perform some sort of the multi-hop reasoning. So this is a data set by some people at Stanford, CMU, and Mila, so called Hotspot QA. So the question is, which one of Ricardo's relatives would become governors from 1983 to 2001? So system actually needs to find out the supporting evidence from the first document that the Ricardo, his brother Adolfo, and another great nephew Abtra have also served as governors of the St. Louis province, and then found out that this person, Adolfo, from the second document, that he actually became governor in 1983 and remained governor up to 2001, and finally figured out this correct answer. And in some even more challenging cases, we actually want to build systems not to only answer one single question based on the document. So this is a data set called Conversational Question Answering Data Set I have worked on last year. So we call it COQA, and I will talk a little bit more later about this data set. So we want to build machine reading systems to not only just answer one single question, but actually can answer a list of the questions in a conversational context. For example, what are the candidates running for? The system returns governor. And the second question, where? And the system can answer Virginia, and so on. So I want to, here I give you some examples that actually the problems, the machine reading problems that we are actually trying to tackle today. So next, I would like to give you a brief history of the reading comprehension. So reading comprehension is actually not a new field at all. As early as 1970s, so a lot of like the AI people already tried to build like a machine reading comprehension systems to tackle the reading comprehension problems. But most of the early work actually based on the scripts or like the rule-based systems. So this field has been revived in 1999 by Lin and Hertman by this by proposing that we actually need to build computer programs to solve this reading comprehension test for the third year to 6th year grade children. And this field has been also revived a little bit in 2013 with this data set MC test from Microsoft. And the people start to try to build some supervised machine reading systems to solve these problems. And around the time of 2015, we finally have some like feature-based machine learning systems try to solve this problem. So what I want to highlight today especially is that machine reading as a field actually has been really kind of like revived and has been kind of a new field since the end of 2015 and 2016. This is actually mostly because today we have the ability to create a lot of large supervised data sets, like some examples I showed earlier, that actually can allow us to build deep neural networks to train on this data set and achieve really impressive performance. So here is a list of the machine reading data sets this community has accumulated, has built over the last few years. I'm pretty sure that I still missed a lot of data sets because there are really too many that I really cannot track. So you can see that in 2013, we have this MC test data set. And in 2015, we have the BBC and Daily Mail data set. But years over years, we have more and more data sets in this form, that document question answer, that trying to tackle different challenges. And we have more and more data sets that actually can allow us to train the deep neural models. So the progress has been also extremely fast. So this is a figure on the Stanford question answering data set of version 1.1. So you can see that when this data set was first released in 2016, in the middle of 2016, unknown neural models was only able to achieve the performance of 51. And after just 2 years, so we got a human performance like over 90% on this data set. And this data set just was sold in 2 years. So this progress has been incredibly rapid, and we have seen a lot of the progress on that. So next, I would like to talk about a project we built in 2017. So this project we call it DrQA. This is a joint work with Adam and Jason and Anton at Facebook. So when I look back, this project has already been almost 2 years now. And it is actually nowhere still close to the state of the art. But it actually was so you can also see that how fast this field is actually moving. So it was actually pretty much the first attempt that we actually really want to achieve this paradigm of machine reading, that we want to bring the machine reading systems, the neural machine reading systems back to the big picture of the open domain question answering, and combine it with some traditional information retrieval solutions. So the big question we want to ask at the time is that, can we actually build a system that can actually read from the whole Wikipedia and answer the open domain questions? So compared to highly engineered open domain question answering systems, this system is actually very simple and a very elegant solution framework. So basically, it consists of 2 stages. That, given the whole English Wikipedia, which consists of 5 million Wikipedia articles, and we take a question like, how many of the Warsaw's inhabitants spoke Polish in 1933? And the first stage of this system is actually IR solution that we call the document retrieval module, that try to take this question and retrieve the top 5 or top 10 relevant articles from the Wikipedia. And the second stage of this system, we call it document reader. It's actually a deep neural model that try to take the paragraphs from this retrieved Wikipedia articles and try to answer questions based on the Wikipedia article, and finally return the answer like this. So we think the DrQA is actually the first attempt that we want to combine the information retrieval and also the machine reading in this open domain question answering setting. So for the information retrieval component, we use a non-machine learning component like TF-IDF-based method with bigram hashing. And this module is able to achieve 70% to 86% of the precision that these top 5 articles actually can contain the answers that we are actually going to evaluate on. So for the machine reading component, we used a model that we can build in 2017. We called Stanford Attentive Reader. It's actually, I will talk about in the next slide. So this model is able to achieve the 70% accuracy on score. So we also at the time we attempt to use some multitask learning with distantly supervised question answering data. As I said, the DrQA system is not really the state of the art for now, but this is actually pretty much the best we can do in 2017. So I want to talk briefly about what this distant supervision is. So we have talked about distant supervision a couple times at this conference. But here, what I mean by distant supervision is that we actually can create the machine reading data sets in the form of the document question answer based on the question answer pair. So we take an existing question answer pair from like track. What US state's motto is life free or die? And the answer is New Hampshire. And we can use a retrieval module to find out this Wikipedia article paragraph which contains the answer. Then we can actually construct an example for this distantly supervised training. So the system we built in 2017 called Stanford Attentive Reader. I'm not going into detail of this, and I don't have time to go into details because I also have a much better model to talk about in the next few slides. So the system, the reader component, the neural model we built at the time is basically like this. So we take the question, the passage, and we use the word embeddings to represent the question answer, passage and question. We parse them through like several layers of the LSTMs, and we build some contextual representations, and try to build some attention between the question and the passage. And finally, we can make prediction using the final modeling layer. And this model was able to achieve like 70% exact match score at the time. So to evaluate this DrQA system, we try to what do I mean by open domain question answering? So we really try to see that how well this system can perform with various different resources, or question answering resources. So we evaluate DrQA system using the track open domain question answering data set around 2000. And also we also evaluate them on the several like large-based question answering data sets like web questions and wiki movies. So these questions are supposed to be designed to be answered using like Freebase or the OMDB, the database like this. So this is the performance we got. So we actually demonstrated that the DrQA system was able to answer a wide range of questions precisely. So this is actually a very trendy evaluation that we only consider top one prediction, also the exact match accuracy. So compared to like a state-of-the-art open domain question answering and a really highly engineered question answering system like DrQA, so we are pretty much the performance on the text-based question answering data sets like track. But we were not really there yet for the large-based question answering data set like web questions. So the gap is like 24.3 versus 39.8. So, but I also want to mention that the DrQA system is actually built on top of like multiple different data sources, including actually Freebase and DBpedia. So in the middle of 2017, so we open sourced this system on GitHub, and it actually kicks a lot of interest in academia and industry. So I want to briefly talk about what has been actually improved after that. So DrQA is really just like a prototype that we actually really want to test out if this idea, the bring machine reading system to the open domain question answering actually works or not. So people have keep improving this system. So there's some follow-up work like trying to improve the paragraph selection using reinforcement learning. And people also have tried to create more high-quality question answering data sets. And also, there's a really nice paper from UMass here that people started try to change this TF-IDF-based retrieval module to an actually trainable component. So the performance has been largely increasing over the last 2 years. Actually, the most important point I want to make is the machine reading systems also keep improving over the last 2 years. So this year, there has been work like trying to apply the state-of-the-art machine reading system based on the BERT, and also some like better IR component. That actually this kind of idea can actually be really implemented in this like open domain question answering system, and has been deployed as a chatbot in many different platforms. So I will briefly talk about like what is actually the state-of-the-art machine reading system actually like a reading comprehension system like. So many of you probably have heard about this model BERT. So I was actually really, this result is actually very mind-blowing to me that such a simple model without any like attention layer, complete attention mechanisms can actually achieve so well on a wide range of the machine reading systems. So the system is actually basically works like takes a question, take a passage, and we can just concatenate the question, the passage, as like a long sequence, and just plug them into as a language modeling style way. And then this system is passed through like 12 layers of transformer, but just as like a language model. And then finally, at the top layer, the system is actually can just predict which span in the passage can actually correspond to the answer. And the whole, compared to the previous generation of the neural reading comprehension models, these models actually, the 12 layers of transformer actually can be just pre-trained as a language model from by using large amounts of text. And this model is able to achieve like superhuman performance like 87.4 on the score data set. So this is actually pretty much the standard we can do today. I guess I don't have time to talk about this. I would probably just skip it. But these are like conversational question answering challenges that we built last year at Stanford, and the joint work with Shiva and Chris. But the whole point of this conversational question, the whole point I want to make here is, so last year we really spent like more than 6 months trying to collect this conversational question answering data set. And we spent a couple months trying to build models and also writing up the paper. But the progress on this kind of data sets has been super fast. So as you can see that just like last September, we used the DrQA system that I just described, and also some like the BiDef system on this data set. And this system can achieve the performance like 65 to 70 performance, F1 accuracy. But just after like 6 months, with this, the result of the BERT, so you can see that this data set actually can get like over 20 points improvement, and this data set already also achieves the like human performance. So I want to make a point that so the speed of the advancing machine reading systems actually goes far beyond our expectation. So you probably have seen some news headlines like after these data sets are solved, like AI beats humans at reading, machine reading systems are becoming more conversational. So I actually want to ask, like, so what is still actually left to solve? Shall we still try to follow this paradigm that try to create more bigger and more changed reading comprehension data sets and which requires different types of reasoning, and try to solve all these tasks like one by one. Shall we still, this is the paradigm that we followed in the last few years. Shall we still try to do this in the next few years? So you can argue that there are still many challenge data sets that are still not solved yet, including this jobs data set that really just came out 2 months ago, which requires discrete reasoning, and also this record data set, which try to tackle the common sense reasoning. So you can see that the gap between the current best model and also the human performance is still pretty big. But actually also, but the progress, if you see we have so many leaderboards. So you can see the performance has been also improving quite a bit. Actually, I'm pretty confident that this gap between the state-of-the-art system and the human performance will be will be closing very quickly. And I'm pretty confident that this data sets will be actually solved in a relatively short time. So my question is, if the field is still moving this way, can we actually really achieve the grand goal of the machine reading in a very short, near future? So I want to make lastly, I want to make a few more points about the status of the machine reading. So the first point is, so actually today, if we actually want to build a robust, if we actually want to build a single and a robust machine reading systems that can actually work well on all the machine reading different domains and different data sets is still actually really hard. So this year we are starting this machine reading shared task, and our goal is actually try to test if we can actually build one single machine reading system that can actually do well across all the tasks. So we want to solve not only each individual task, but all the tasks together. So here is pretty much the best model today, that we take the best BERT large model, and we train the model using some of the most important training resources we have in this field. And we can actually see that there's still really a huge gap here. If we want to train systems, so you can see there's a huge gap between the in-domain accuracy and out-of-domain accuracy, especially on some tasks like job, like race. Race is actually more like a exam test. So you can see the gap is still there, and we are not solved yet. The second point I want to make is, I still believe that the ability of the current machine reading systems that perform the discrete reasoning is still pretty limited. So I used this question early in the beginning, that so even the best machine reading system, BERT-based model, is still not able to answer questions like what is the population of the second largest city in California using a text like this. So it really has to understand the text and do perform some sort of discrete reasoning. So these kind of questions are actually still much easier for the structured large bases. So some recent data sets like job are trying to tackle this problem. But I believe that we are able to get there. So one potential solution is to actually add some discrete structure back to the machine reading systems like logic forms. So we actually will have a paper submission tonight at the EMP that trying to partially solve this problem. Okay, the third point is, today we actually still there's sufficient evidence to see that because these machine reading systems actually completely ignore the large structure. So if we actually can still align the large base and the text, so we can still see some gains to achieve the better performance on in the machine reading systems. So finally, I want to make points because the performance of the current machine reading systems is getting better and better, we actually, we still believe that we actually really want to build the structured large base. I deeply believe that machine reading systems can actually contribute to the large base construction. So here is like ideas that Almer and other UW folks developed in 2017, but I feel like there isn't too much work yet in that direction. Basically, the idea is that if you have a really good machine reading system, and if you want to do logic-based construction, for example, from this text to the info box on the right, you can actually write a question about the relation. You can write a question like from the screenplay by to who wrote the film, a change of habit. And by using the state-of-the-art, the best machine reading system today, these are kind of new results that we can show that this kind of system already can achieve like 72.3% accuracy just on this relation extraction data set. So I will just quickly sum up. So I think we have made like huge progress in the field of machine reading in the last few years because of the large data set and also the expressive deep neural models. And these machine reading systems will get better and better in the next few years and will become a crucial component in question answering dialogue systems. However, it's still really hard today to build one single machine reading system, which is actually robust and accurate across different domains and distributions. And the ability of the current machine reading systems at performing discrete reasoning is still pretty limited. So tomorrow we'll have this workshop. I'm sure that there'll be a lot of discussions around on this topic. So I will end up here, and thanks. Here's my contact, and I'm happy to take questions if you have time. Thanks.
Maybe we have time for one question.
So first of all, I think like transfer learning and multitask learning will be a very important direction in this area in the next few years. That how can we leverage whatever resources we have to train on question answering on the machine reading systems that can actually transfer to the other domains tasks. And I talk about it's still really hard to build one single system to perform across all the tasks. My starting point is that we actually really want to build a unified model, to do like open domain question answering. Eventually, we actually want to unified model that can solve all types of problems together. So we get accuracies on improvements on different sort of tasks, but eventually we actually want to have like a unified system. Thanks.
Let's thank